Welcome to The Deep Dive, the show where we grab a stack of the latest research, distill the most important insights, and deliver them to you with, hopefully, just enough humor to keep you hooked.
We try our best.
Look around you these days, and you'll see generative AI, well, everywhere. It's in breathtaking creative tools that can spin up images or music in seconds, to incredibly efficient customer service bots that anticipate your needs, even personalized learning platforms.
It honestly feels like a touch of magic sometimes, doesn't it?
It really does.
Yeah.
But have you ever paused to really wonder, how does this magic actually work behind the curtain?
Yeah, what's really going on?
How do these AI models become so astonishingly capable? And what are the hidden challenges that the engineers and researchers behind them are constantly wrestling with?
Right.
This deep dive is your shortcut to understanding the cutting edge of what makes generative AI truly tick.
And today, our guide through this complex, but I think fascinating landscape is Rick Sperr's comprehensive report, The Scaling Dichotomy, Navigating the Frontier of Generative AI Architecture, Efficiency, and Performance.
Wow.
And our mission really is to unpack the fundamental, often intense tension that lies at the very heart of generative AI development. It's this relentless push for ever larger, more powerful, and more capable models, constantly balanced against the absolutely critical need for efficiency. Efficiency in how these powerful systems are not just built, but also how they're trained and ultimately run in the real world.
Got it. So we're embarking on a journey today. We'll begin by laying down some foundational concepts like the empirical laws that dictate how these models learn and how they achieve their impressive scale.
The basics, yeah.
Then we're going to dive deep into some truly groundbreaking architectural innovations, the clever engineering solutions that are reshaping the entire field.
Some really smart stuff there.
Yeah. And finally, we'll cast our gaze toward the exciting and sometimes uncertain future trajectory of AI development. Get ready for some serious aha moments, I hope, and practical insights that will give you a much clearer understanding of the profound forces driving the AI revolution that's happening all around us.
Yeah, and to give you a bit of a mental roadmap for our discussion, we'll first thoroughly explore the evolving understanding of what are known as scaling laws.
Okay.
And then we'll delve into the fascinating and at times pretty controversial debate surrounding what researchers refer to as emergent abilities in these models.
The emergence debate. Always interesting.
Always. From there, we'll make a pivotal transition into understanding transformative architectures, specifically focusing on mixture of experts, or MOE,
MOE, right?
and retrieval-augmented generation, often just called RAG.
RAG. Heard a lot about that, too.
Exactly. We'll then wrap up by analyzing how strategic trade-offs define what an optimal balance truly means in the intricate world of AI design. It's all about trade-offs.
All right, let's dig into this because it's where the foundational principles of modern AI really begin. For years, the guiding principle, almost an article of faith, in generative AI development, has been bigger is better.
Pretty much, yeah.
And this isn't just some theoretical idea. It's an empirical observation, a robust power law relationship that consistently shows predictably better performance in generative AI models.
Right. It's based on data.
And this improvement comes from methodically increasing three key factors. The sheer number of model parameters, let's call that N, the size of the training dataset used, D, and the computational budget dedicated to training, C.
N, D, and C. The big three.
What's truly astonishing, as Rick Sperr highlights, is that this remarkably consistent relationship has been observed to hold true across more than 7 orders of magnitude in terms of model scale.
7 orders of magnitude. Think about that for a moment. The consistency of this pattern, from tiny models to the absolute giants we see today, is genuinely incredible.
It really is.
Indeed. The foundational principle here, as Rick Sperr's report thoroughly details, is that performance in neural language models, which is typically measured by something called cross-entropy loss.
Which is basically how well it predicts the next word, right?
Essentially, yes. How accurately the model predicts the very next word or token in a sequence. And this loss improves predictably as a power law function of those 3 factors we mentioned. Model parameters, N, training dataset size, D, and the computational budget, C, which is often measured in floating point operations, or FLOPs.
Right, the FLOPs.
This predictable, albeit incredibly expensive recipe for progress, has been the bedrock, the fundamental playbook for the industry's rapid and massive push towards ever larger models.
And leading that charge way back in 2020 was OpenAI with their seminal paper by Kaplan and his team.
The Kaplan paper.
This paper didn't just observe these power law relationships, it formalized them for transformer models and truly set the initial paradigm for how the entire industry approached scaling. It was a groundbreaking moment, really.
Yes, absolutely. And their primary finding, which was hugely influential at the time, was that for a fixed compute budget, meaning if you only had a certain amount of processing power and time model size, N was identified as the primary driver of performance.
Model size was king.
It was found to be significantly more impactful than simply increasing the dataset size. This led to a very clear and, at the time, widely adopted recommendation: build very, very large models.
Go big?
Train them on a relatively modest amount of data, and often stop the training well before the model had fully converged on that data.
Why stop early?
Because the biggest gains were seen by just adding more parameters. Scale was the priority.
I remember that era. This conclusion was a monumental catalyst, wasn't it?
Yeah.
It truly sparked a massive arms race across the entire AI industry.
Oh, absolutely. Everyone became obsessed with maximizing parameter counts.
And we saw this exemplified by models like the 175 billion parameter GPT-3 and DeepMind's own staggering 280 billion parameter Gopher. So if we break this down, this meant a frantic push for hardware with massive memory, often called VRAM, just to be able to hold these colossal models, right?
Exactly. The prevailing belief was the more parameters, the better the model. Even if you weren't feeding them absolutely endless amounts of data, the scale itself was seen as the magic ingredient.
The parameter count was the headline number everyone chased.
However, this initial paradigm, this bigger is better mantra, faced a profound and utterly game-changing recalibration in 2022 with DeepMind's chinchilla scaling laws.
Ah, chinchilla. This really shook things up.
It did. These new findings, which were painstakingly derived from training over 400 distinct models
400 models.
and visualizing what they called isoflop curves, which essentially map model performance for a fixed computational budget, revealed a fundamentally different and far more optimal allocation of resources.
So they weren't just theorizing, they were running tons of experiments.
Exactly. It showed that the industry had been chasing the wrong dragon, at least partially.
Okay, this is where things take a fascinating turn. So DeepMind comes in and says, hold on, you're doing it wrong. How did they even figure that out? What did Chinchilla tell us that was so profoundly different from Kaplan's findings?
Well, Chinchilla fundamentally shifted our understanding by demonstrating that for optimal efficiency, model size, N, and training dataset size, D, should be scaled in approximately equal proportions.
Equal proportions, not just bigger N.
Right. This was a monumental revelation because it immediately implied that many of the largest models of that era, including the groundbreaking GPT-3 and DeepMind's own Gopher,
Previous champions?
were significantly undertrained. They were, in essence, simply too large for the amount of data they had been trained on.
It was like building a massive library, but only filling a quarter of its shelves, you said.
Exactly that analogy. Lots of potential capacity, but not enough knowledge put into it relative to its size.
And how did they prove this concretely? Did they build a new model specifically to validate this new theory?
Precisely. To definitively validate their new law, DeepMind trained the 70 billion parameter chinchilla model on an astounding 1.4 trillion tokens.
1.4 trillion tokens. That's a massive data set.
Huge. And as their new law powerfully predicted, this 70 billion parameter chinchilla consistently outperformed the much larger 280 billion parameter Gopher model.
The smaller model beat the bigger one.
Yes, the one which, notably, had only been trained on 300 billion tokens. And critically, both models were trained with the exact same computational budget.
Same compute, different allocation.
Correct. This wasn't just a marginal improvement. It was a clear, unambiguous demonstration of a far more efficient path to achieving state-of-the-art performance. It showed you could do more with less if you allocated your resources wisely between model size and data size.
So this wasn't just an academic correction then, was it? Rick Spear really emphasizes this in his report, describing it as a fundamental multi-billion-dollar recalibration of AI development strategy.
Absolutely. It wasn't just about different numbers on a chart. It was about entire business models being potentially upended and billions in R&D dollars needing to be reallocated.
Suddenly, the race wasn't just for the biggest model, but for the best data pipeline, right? A subtle but profound shift. What were those profound second-order effects?
You're absolutely right. The ripple effects were enormous. The earlier Kaplan laws had incentivized a model size at all costs approach, driving demand for that very specific hardware with massive VRAM you mentioned.
Right, the VRAM obsession.
The chinchilla laws revealed this is computationally inefficient and fundamentally altered the strategic landscape. The new optimal strategy, which suggests training smaller models on vastly more data, has had two profound second-order effects.
Okay, what's the first one?
First, high-quality training data, which was once perhaps seen as secondary to sheer model size, suddenly became the primary limiting factor for progress.
Data became the bottleneck.
Exactly. This elevated its strategic importance dramatically, emphasizing the critical need for robust data acquisition, meticulous curation, and novel methods for synthetic data generation. Companies realized that data is the new oil was maybe even an understatement for AI.
So data sourcing and quality became paramount. And the second effect must be massive for practical commercial applications, right? Because cost is always a factor when you move from research to deployment.
It truly is. The resulting models, being smaller for a given performance level, are significantly cheaper to operate during inference.
Inference being when the model is actually used, not trained.
Correct. Think about it. Every time someone uses ChatGPT or any other AI model, that's an inference cost. If the model is smaller yet just as capable, the cost per query plummets.
That's huge for businesses wanting to use these tools.
It's a crucial factor for commercial viability and widespread deployment, and it directly benefits you, the user, in terms of accessible and affordable AI services. It makes advanced AI capabilities available to a much broader audience and for a much wider array of applications.
It shifts the entire economic model of AI from exclusive, massive labs to something potentially more democratized, a more distributed ecosystem, perhaps.
Precisely.
So we've established that there's a predictable, albeit constantly refined, way to scale these models to achieve better performance. That's the science, the scaling laws.
Mm-hmm.
But what about the truly unpredictable capabilities that seem to emerge as models grow? That feels less like a smooth curve and more like a sudden, almost magical leap, doesn't it?
Right. It's not always just gradual improvement.
This is a really fascinating and, for some, maybe a somewhat unsettling aspect of AI development.
The phenomenon of emergent abilities is indeed one of the most intriguing and debated topics in AI right now. It refers to the observation that certain complex capabilities.
Like what, for example?
Well, like the ability to perform multi-step arithmetic, or maybe even answer grade school science questions with decent accuracy. These abilities are simply not present in smaller models. They don't seem to exist at smaller scales.
No, they just appear.
They only appear, often quite unpredictably and sharply, after a critical scale threshold is crossed. This suggests that you can't just extrapolate from smaller models to predict the full capabilities of scaled-up systems.
Which adds a layer of genuine unpredictability to AI development.
It does, and it raises questions about what else might unexpectedly appear as models get even bigger.
But there's a powerful and quite compelling counterargument, isn't there? That these emergent abilities might actually be more of a mirage than true unpredictable leaps.
Exactly. A compelling counterargument suggests these so-called emergent abilities are more of an artifact created by the researcher's choice of evaluation metrics.
Ah, so it's about how we measure them.
That's the core idea. The argument is that the model's underlying performance, for example, its per-token cross-entropy loss that we talked about,
It's basic prediction accuracy.
that actually improves smoothly and predictably with scale, entirely consistent with the scaling laws we just discussed. It's like the model is steadily getting better, but our way of measuring it makes it look like a sudden jump.
Okay, so the underlying performance is smooth, but our measurement makes it look like a sudden jump. Can you walk us through how that optical illusion, if you will, happens?
Well, the argument goes like this. Using nonlinear or discontinuous metrics like accuracy, which demands every single token in an answer to be absolutely correct for any score.
All or nothing.
Right, all or nothing. That can transform this smooth underlying improvement into a sharp, seemingly unpredictable jump.
Give us an example.
Okay, imagine a model trying to answer a multi-digit addition problem like 123 plus 456.
Yeah.
For it to get the answer 579 completely right, the probability of generating each correct digit, the 5, the 7, the 9, must cross a certain threshold.
Right.
Now, even if the individual probabilities for each token, each digit, improve smoothly as the model scales, the probability of the entire sequence being correct can increase dramatically over a very small change in the model's capabilities, right, once that threshold is crossed for all digits.
Ah, I see. The chance of getting all three right jumps up suddenly, even if the chance for each one only improved a little bit.
Precisely. Conversely, if you apply a more continuous metric that awards partial credit, like token edit distance, which measures how many changes are needed to correct an answer.
So it gets points for getting 578 mostly right.
Exactly. Then the sharp emergent leap often disappears, revealing a much more predictable and gradual performance curve.
Wow, that completely reframes how we look at this. It sounds less like the model itself is behaving unpredictably and more like our measurement of its behavior is creating the illusion of a sudden jump.
It's a very strong possibility, yeah.
So where does the debate stand now? Is it settled science that it's just a measurement artifact?
Not entirely settled, which is why it remains such an active area of research and discussion. While metric choice is certainly a powerful explanatory factor, some studies still show that abrupt performance jumps can persist even when using smoother metrics.
Oh, really?
Yeah, suggesting that genuine emergence may still be a reflection of the model's internal learning dynamics, perhaps a kind of phase transition in its learned representations.
So maybe there's something real happening internally, too.
It's possible. Interestingly, Rick Spare's report points out that the pre-training loss, how well the model did during its initial training, independent of its final size, has been identified as a strong predictor of when these abilities develop.
What does that suggest?
It suggests that emergence might be more directly linked to the quality and completeness of the training process itself, rather than purely to a raw increase in scale. It offers a slightly more mechanistic understanding.
This debate has profound implications, especially for the critical field of AI safety, doesn't it?
Absolutely.
Because if these abilities are truly unpredictable, that's a very different scenario than if they're predictable but just measured poorly.
It absolutely does. The implications are stark. If these abilities are truly emergent and fundamentally unpredictable, then AI safety faces a daunting challenge.
How so?
A model might unexpectedly acquire dangerous capabilities, like highly sophisticated deception or manipulation skills, without any warning signs or precursors from smaller-scale versions. This would make anticipating and mitigating risks incredibly difficult.
Like a switch flipping unexpectedly.
Right. However, if these abilities are merely a mirage of metrics, then the problem shifts dramatically. The model's core behavior would remain predictable via scaling laws.
So the danger isn't the model itself being unpredictable.
The danger then lies not in unpredictable model behavior itself, but rather in our failure to choose evaluation metrics that accurately and continuously reflect the capabilities we truly care about, both the beneficial ones and the potentially harmful ones.
This raises a profoundly important question for anyone building or deploying AI systems.
Yeah.
How do we ensure we're measuring what truly matters?
Exactly.
Because if our metrics are misleading, we could be completely blindsided by a model's capabilities, or maybe even its lack thereof in critical areas.
Precisely. This suggests a critical need to shift AI safety research away from trying to predict unknowable phase transitions and towards developing incredibly high-resolution continuous evaluation suites.
Better measurement tools.
Yes, suites capable of detecting subtle, incremental changes in a model's capability long before they cross a dangerous threshold that might only be defined by a coarse, real-world metric like passes a bar exam or something similar.
It's about getting much more granular and transparent in our assessment, understanding the underlying mechanisms of improvement rather than just the surface-level performance.
That's the goal, yeah.
So whether through brute force scaling following predictable laws or these surprising, seemingly emergent leaps that might be an illusion of our metrics, models are undoubtedly getting more and more capable.
No question about that.
But the sheer cost, as we've already touched upon, is immense. It's a fundamental constraint.
It really is.
This leads us perfectly into the crucial architectural innovations designed to achieve massive scale benefits without the proportional cost. This is where the engineering really starts to get creative, finding clever ways to optimize.
Indeed. As the scaling laws clarified the relationship between resources and performance, the sheer cost of applying them directly created a new, urgent imperative: architectural efficiency.
We need smarter designs, not just bigger ones.
Exactly. The industry began to explore how to achieve the benefits of massive model scale, that incredible knowledge and reasoning capacity, without a proportional increase in the astronomical computational cost.
And mixture of experts, MOE, is a key part of that story.
And the mixture of experts, or MOE architecture, has rapidly emerged as the leading, arguably most transformative solution to this challenge. It fundamentally changes how computation happens within the model.
Let's talk about that. What makes traditional models, what you call dense or monolithic models, hit this computational wall that makes them so incredibly expensive to run at scale?
Okay, so traditional transformer models are what we call dense or monolithic. This means that every single parameter in the model, and remember, these can be in the hundreds of billions now.
Every single one.
Every single one is activated and participates in the computations for every single input token.
So for every word processed, the entire model lights up, computationally speaking.
Effectively, yes. It's like activating its entire brain for every tiny piece of information. As models began to scale into the hundreds of billions of parameters, the computational cost, measured in FLOPs, for just one forward pass, just one instance of processing an input, became truly immense.
Creating that computational wall.
Exactly, making both training and critically inference actually using the model prohibitively expensive, energy-intensive, and often very slow.
So MOE offers a way around this wall. How does it work? How does it manage to reduce that active computation without losing all that knowledge packed into the parameters?
Mo addresses this problem by introducing what's known as sparsity through a clever divide-and-conquer strategy, often called conditional computation.
Sparsity, meaning not everything is active.
Right. Instead of one massive monolithic feed-forward network, or FFN, layer, which is a standard component in a transformer and MOE layer, contains multiple smaller, independent FFNs, which we call experts.
Wait, multiple mini networks instead of one giant one.
Precisely. And the genius here is that for each input token, a lightweight gating network, or router.
A router, like for internet traffic?
Sort of, yeah. It dynamically and intelligently selects only a small subset of these experts, for example, maybe 2 out of 8 total experts, or 4 out of 16, to process that specific token.
So only a few experts work on each piece of input.
Correct. And the beauty is that the inactive experts simply remain dormant, saving a vast, vast amount of computation.
That sounds incredibly clever. So not all parts of the model are working all the time. It's like a specialized team. Can you break down the actual anatomy of an OE model for us? What are its core components and how do they interact?
Certainly. An MOE layer is fundamentally composed of 2 primary components, the experts and the router.
Okay.
The expert subnetworks are typically independent neural networks, often just standard FFN blocks like you'd find in a dense model, but smaller. These are the workhorses that do the actual computation on the input.
Got it. And you gave an example earlier.
Yeah, take a model like Mixtral 8x7b as an excellent example. Each transformer layer within Mixtral contains 8 distinct FFN experts. This MOE block effectively replaces the single large FFN block you'd find in a traditional dense transformer.
So instead of one big FFN, you have 8 smaller specialized ones in that layer.
Exactly.
And the router, what does that do? Is it like a traffic controller for the tokens?
Precisely. The gating network, or router, is a small, computationally inexpensive neural network. Its job is to take a token's representation, essentially the model's understanding of that word or piece of data at that point, as input, and then output a probability distribution over all the available experts. Basically, it decides how relevant each expert is for this specific token.
And then it picks the best ones.
Right. A routing strategy, most commonly a top K approach, is then applied to select the K experts with the highest probabilities. For instance, if K2, it picks the 2 experts most likely to be helpful for that specific token.
And what happens with their outputs?
The outputs of these selected experts are then combined, usually via a weighted sum based on the router's probabilities, to produce the final output of the layer. It really is like a very smart traffic controller directing information to the most relevant specialist.
This seems to solve a core problem, elegantly decoupling the total size of the model from the computational cost of actually running it. That's a huge breakthrough.
That's the key innovation of MOE and why it's so disruptive. It explicitly decouples the total parameter count from the active parameter count.
Total versus active. Explain that difference again.
The total number of parameters serves as a measure of the model's overall knowledge capacity. It represents the vast library of information and patterns the model has learned. For instance, the Mixtral 8x7b model has approximately 47 billion total parameters.
Okay, that's its potential knowledge.
But the number of active parameters for any given token processed at any given moment determines the computational cost of inference. For Mixtral 8x7b, only about 13 billion parameters are active per token.
Much less than the total 47 billion.
way less. This allows a MOE model to achieve the performance, the reasoning power, of a much larger, dense model, while having an inference speed and, critically, a cost comparable to a much smaller, dense model. It's a remarkable efficiency gain.
What's fascinating here is it sounds like MOE represents a fundamental shift not just in efficiency, but in how these models process information internally. It suggests a move away from brute force pattern matching towards something more nuanced, maybe.
It absolutely does. A dense transformer applies the exact same FFN block to every single token, regardless of its content or context. It's a uniform processing pipeline.
One size fits all.
Pretty much.
Okay.
But a MOE model, through its intelligent router, learns to identify different types of inputs, perhaps distinguishing between tokens related to syntax versus semantics, or maybe even identifying different languages within a mixed input.
So it can tell what kind of information it's looking at.
That's the idea. It then routes these distinct types of information to different specialized computational pathways, or experts. This implies that the model is learning a sophisticated form of internal task decomposition.
Breaking the problem down internally.
Exactly. Where certain experts become highly specialized for particular types of information or computational subtasks. And this modularity is a significant step towards more interpretable AI.
How so? How does it help interpretability?
Well, by analyzing which experts are activated for which tokens, you can begin to gain some understanding of how the model is processing and reasoning about information. It potentially moves us away from the complete black box problem, offering glimpses into its internal workings.
That's a huge step toward making AI less of a black box. But surely there are complex training challenges with an architecture this intelligent, aren't there? You can't be all smooth sailing.
Oh, there are definitely unique training challenges that are not present, or at least not as pronounced, in dense models. A primary challenge is load imbalance.
Load and balance, what's that?
That's where the gating network, over the course of training, can develop a preference for a few popular experts, routing a disproportionate number of tokens to them.
So some experts get overworked and others sit idle.
Precisely. This leaves other experts undertrained and underutilized, negating the benefit of having a large pool of specialists and essentially wasting compute and capacity.
How do they fix that?
To counteract this, an auxiliary load balancing loss is often added to the model's main loss function. This specifically penalizes uneven distributions and encourages the router to spread tokens more evenly across all available experts during training.
So it's like making sure all the specialized librarians get enough work. What about stability? I can imagine all these routing decisions might make training a bit chaotic sometimes.
You're right. The discrete routing decisions in MOE, where a token is specifically sent to one or two experts and not others, can indeed lead to training instabilities, making the optimization landscape more complex compared to dense models.
And fine-tuning. Adapting it for specific tasks.
Furthermore, fine-tuning MOE models, which is the process of adapting a pre-trained model to a new, specific task, can be more complex than their dense counterparts and potentially more prone to overfitting.
Why overfitting?
Because only a fraction of the model's vast weights are updated for any given training example during fine-tuning, which can sometimes lead it to specialize too narrowly. Research has shown that strategies like fine-tuning only the non-MOE or dense parameters or carefully leveraging instruction tuning can yield more stable and effective results, making them robust enough for real-world deployment.
Okay, so there are ways to manage it. Now, MOE drastically reduces the computational cost, the FCLOPs, which is fantastic for operations. But you mentioned earlier that those massive total parameter counts still have to be stored somewhere. Does MOE actually reduce the memory requirements, the VRAM? Because that's a big constraint for deployment, right?
That's a critical trade-off of the MOE design, and it's important to be very clear about it. While it significantly reduces computational costs in terms of FLOPs, it does not reduce memory requirements in terms of VRAM.
Ah, okay, so the memory footprint stays big.
Exactly. All expert parameters must be loaded into memory, your GPU's VRAM, for the router to be able to select from them, even if only a few are actively used at any given time.
So even if only 13 billion parameters are active in Mixtrol, you still need enough VRAM to hold all 47 billion.
Correct. This means a MOE model with, say, 140 billion total parameters requires a similar amount of VRAM as a 140 billion parameter dense model. This is true even if its inference speed is closer to that of a 40 billion parameter dense model.
That's a huge deal for anyone without massive hardware.
It is. This makes MOE a hardware-aware architecture that explicitly trades increased memory footprint for reduced computational demand. It's a highly favorable trade-off in compute-bound scenarios, like pre-training huge models in large data centers.
Where compute is the main cost.
Right. But it can be a significant challenge in memory-constrained environments, like deploying on a consumer-grade GPU or an edge device where VRAM is a strict and expensive bottleneck.
So it's not a magic bullet for every scenario, particularly if you're trying to run it on limited hardware. I've also heard about different, more advanced routing strategies. Are there ways to improve the routing beyond just sending a token to the top K experts?
Yes, absolutely. To address some of these challenges, like load balancing and further optimize performance, various alternative routing strategies have been developed beyond the simple top K routing.
Like what?
For instance, there's expert choice routing. This flips the logic. Instead of tokens choosing experts, the experts, which have a predetermined capacity, actually select the top tokens they are best suited to process.
Oh, interesting. The experts pick the tokens.
Yeah. This approach guarantees perfectly balanced load across all experts, which can be beneficial for training stability and ensuring all experts get utilized effectively.
And other approaches.
Some cutting-edge models, like DeepSeek V2, also introduce a fascinating hybrid approach. They have shared experts that are always active, learning core, general-purpose knowledge, common to all tasks.
Like a foundation.
Exactly. And then they have routed experts that learn more specialized peripheral information, allowing the model to be incredibly versatile and efficient by combining general knowledge with specific expertise.
That's a brilliant way to make computation itself more efficient within the model. But what about making knowledge itself more efficient and, crucially, more up-to-date?
Right, the knowledge problem.
Because a model trained in 2023 won't know about events in 2024 unless you retrain it entirely, which is super expensive. That's where Retrieval-Augmented Generation, or RAG, comes in, right?
Precisely. The second major efficiency strategy, and one that is hugely impactful for practical applications, involves improving a model's knowledge and factuality without the need for constant, costly, and time-consuming retraining.
Avoiding those massive training runs.
Exactly. This approach centers on a fundamental distinction between the knowledge stored implicitly within a model's parameters, which we call parametric memory.
The knowledge baked into the model weights.
Right. And knowledge that is explicitly retrieved from an external, continuously updated source, which is referred to as non-parametric memory.
External knowledge.
Okay.
Okay. So what exactly are the limitations of that parametric memory that a standard large language model, or LLM, has? Why is it not enough for many real-world use cases?
Well, a standard LLM's knowledge is implicitly stored within its network weights, its parametric memory. This knowledge is inherently static, or frozen.
Frozen in time.
It's captured at the very end of the training period and cannot be updated with new information without retraining or fine-tuning the entire model, which, as we've discussed, is incredibly costly in terms of compute, time, and money.
So it gets out of date fast.
Very fast. This static nature means that models trained on data up to, say, early 2023 cannot answer questions about events that occurred afterward, leading to outdated, irrelevant, or even wildly incorrect responses.
And this directly leads to a problem we've all heard about, which can be quite frustrating for users. Hallucinations.
Yes, absolutely. Because this parametric knowledge is essentially a statistical representation of the training data rather than a structured database of facts, LLMs are unfortunately prone to hallucination.
Making things up, basically.
They can confidently generate plausible-sounding but factually incorrect or nonsensical information, especially when queried on topics outside their core training distribution or when faced with ambiguity. There is no built-in mechanism for a purely parametric model to fact-check its own output or verify information against a trusted external source.
It just predicts the next word, plausible or not.
It simply generates what it predicts is the most probable sequence of words based on its training, whether that sequence reflects reality or not.
So ROG is presented as the solution to this fundamental knowledge dilemma. How does it augment an LLM, and how does it make it smarter without changing its core brain?
Retrieval-Augmented Generation, or RI, directly addresses these parametric limitations by augmenting an LLM with non-parametric dynamic memory.
That external knowledge base.
Right. It achieves this by connecting the model to an external, authoritative, and continuously updated knowledge base at inference time, meaning right when a user asks a question.
So it happens on the fly.
Exactly. The entire system operates on a straightforward, yet incredibly powerful retrieve-then-generate principle. Instead of just trying to remember the answer from its internal weights, it first tries to find relevant information externally.
Retrieve first, then generate. Makes intuitive sense.
Yeah.
So let's break down that pipeline. How does AGA actually work in practice, step by step, for a user query?
Okay. The RGAD pipeline typically consists of three main stages. First, you have the indexing stage.
Setting up the knowledge base.
Right. This involves collecting, cleaning, and carefully segmenting a corpus of external documents. Think corporate wikis, comprehensive product manuals, recent news articles, or even private internal research papers into smaller, more manageable chunks.
Breaking down the documents.
Yes. Then an embedding model plays a crucial role. It converts each of these text chunks into a numerical vector, a list of numbers that precisely captures its semantic meaning.
Turning words into math.
Essentially, yes. These vectors are then stored in a spiralized vector database, which is optimized for incredibly high-speed similarity searches, allowing you to quickly find concepts that are semantically close, even if they don't use the exact same words.
Okay, so you've pre-processed all your knowledge into these numerical vectors, making it searchable by meaning. What happens when a user asks a question then?
That's the second stage, retrieval. When a user submits a query, that query is also converted into a vector using the exact same embedding model used during indexing. Consistency is key there.
So the question becomes a vector too.
Right. The system then performs an incredibly fast similarity search, for example, using a metric like cosine similarity within the vector database. Its goal is to find the document chunks whose meanings are most relevant or similar to the user's query.
It finds the best matching pieces of text from the external source.
Exactly. It's like a lightning-fast semantic search engine for your own personal curated knowledge base.
And finally, the generation part. This is where the LLM comes back in, right?
Yeah.
It takes these retrieved pieces of information and crafts an answer.
Precisely. The third stage is generation. The retrieved chunks of text, the relevant facts or snippets from your external knowledge base, are then concatenated, basically stitched together, with the original user prompt.
So the prompt gets longer, including the retrieved info.
Correct. This concatenation provides the large language model with rich, relevant, and crucially up-to-date context directly within its input window. The LLM then generates a response that is grounded in this provided information, synthesizing an answer based directly on the retrieved facts rather than solely on its potentially outdated pre-trained knowledge.
It essentially gives the LLM a fresh set of facts relevant to the question every single time.
That's a great way to put it.
This sounds like a massive leap forward for the practical, real-world applications of AI, especially in enterprise settings where accuracy and currency are paramount. What are the main benefits you see from adopting RAG?
The primary benefits of RAG are indeed transformative. You see significant improvements in factual accuracy and a marked reduction in those frustrating hallucinations we discussed.
Less making things up.
Much less. Crucially, it provides the ability to offer up-to-date information without requiring costly and frequent retraining of the entire model.
That's huge.
It means you can keep your AI current with the latest news or internal data by simply updating the external database, which is far, far more efficient than retraining an LLM.
Just update the documents.
Right. And perhaps one of the most powerful benefits is traceability. The system can often cite the specific sources it used from the knowledge base to generate an answer.
Show its work.
Exactly. Which profoundly enhances user trust and allows for easy verification and fact-checking. This is huge for reliability, especially in high-stakes domains.
If we connect this to the bigger picture, RA sounds like it's fundamentally changing the LLM's role. Maybe from an all-knowing oracle to something more akin to a brilliant reasoning engine with access to an incredible, up-to-date library.
It is a profound architectural shift. You've hit the nail on the head. RA effectively decouples the LLM's role as a reasoning engine from its previous combined role as a knowledge repository.
Separating reasoning from remembering.
In a purely parametric model, these two functions are inextricably linked within the model's vast weights. RA externalizes the knowledge into a standard, manageable database. The LLM's primary task shifts from trying to remember the answer to reasoning over the provided context to formulate an answer.
That must have massive implications for businesses adopting AI.
It really does. It transforms the AI problem from a highly specialized, computationally expensive model training challenge into a much more familiar and manageable data engineering problem of simply building and maintaining that external knowledge base. It makes AI far more accessible and adaptable for businesses of all sizes.
RAG sounds incredibly powerful, and we often hear it discussed alongside fine-tuning. Both seem to specialize models or make them better at specific tasks, but they operate very differently, don't they?
They do operate very differently.
How do they compare And when would you choose one over the other? It seems like a fundamental decision point for anyone building with AI.
That's an excellent point, and it's a crucial distinction for practical AI development. Both RAG and fine-tuning aim to improve a model's performance on specific tasks, but they achieve this through fundamentally different mechanisms and are indeed suited for very different purposes.
And sometimes they can work together.
It's not always an either situation. Sometimes they can even complement each other quite effectively.
Okay, let's start with fine-tuning. What is it fundamentally, and what are its strengths and weaknesses?
Fine-tuning involves further training a pre-trained model on a smaller, typically domain-specific dataset. This process modifies the model's parametric memory, meaning it actually tweaks the internal weights and connections of the neural network itself.
It changes the core model.
Yes. This allows it to adapt its internal knowledge, its specific conversational style, or to truly internalize the nuances of specialized vocabulary within a particular field like medicine or law.
So it's best for teaching it new skills or styles.
It's generally best for teaching a model a new skill, for instance, how to summarize legal documents in a particular format, or how to speak with a specific brand voice. It genuinely adapts the model's internal behavior and knowledge patterns.
What are the downsides?
Well, it comes with a high computational and financial cost for the training itself, and any retraining needed to update its internal knowledge is also expensive. And crucially, the knowledge it incorporates is static. It requires retraining the entire model again to incorporate new factual information, which is a continuous, potentially very expensive cycle.
So fine-tuning changes the model itself, costs a lot, and the knowledge gets stale. How does RGAG compare on those points? What are its unique advantages, and where might it fall short?
RAG, in contrast, does not change the core model at all. The underlying LLM stays the same. It involves providing knowledge as context at inference time, essentially giving the model a temporary external memory for each query.
So it's about providing external facts, not changing internal skills.
Exactly. It is best suited for tasks that require access to a large dynamic body of factual information that changes frequently, like current events, rapidly updating product inventories, or a company's internal knowledge base that's constantly being revised.
And the cost and updates.
RAG is generally far more cost-effective and much easier to keep current than continuous fine-tuning, as updating the knowledge base simply requires modifying the external database, not altering the massive model itself. The knowledge is dynamic and easily refreshed.
What are the trade-offs with RAG?
The trade-offs, however, include the added latency of the retrieval step before generation. It needs to go out and find the information, which takes little time. And the operational complexity of building and maintaining that external knowledge base effectively. Ensuring it's clean, organized, and constantly updated is a data management task in itself.
So if I'm building an AI, it sounds like fine-tuning is about teaching the model to think or talk differently, to learn new skills or styles, while RAG is about giving it access to the most up-to-date facts it needs to solve a problem using those skills.
That's a very good summary. Fine-tuning adjusts how it processes, RAG adjusts what it knows at that moment.
But is there any challenge when trying to combine these two approaches? Does the model always prioritize the retrieved context from RAG? Does it listen to the facts you give it?
That's a very insightful question, and it highlights a significant interplay challenge. While RAG is powerful, research shows that large language models can exhibit a strong bias towards their deeply ingrained, pre-trained parametric knowledge.
Its old habits die hard.
You could say that. Sometimes they ignore or even subtly override the retrieved context, especially when the two sources of information conflict. This is often referred to as parametric bias.
So it might trust its old training more than the new facts.
It can happen. This raises an important point. Simply providing the right information through RBAG is not always sufficient. The model must also be carefully prompted, or in some cases even fine-tuned specifically, to ensure it reliably prioritizes and integrates that retrieved information.
You might need to explicitly tell it, hey, pay attention to these facts I just gave you.
Essentially, yes. Especially in scenarios where its internal memory might offer a different, potentially incorrect answer. You need to guide its attention.
So what does this all mean for you if you're navigating this landscape, whether as a developer, a business leader, or even just a curious user? It means choosing the right tool for the job.
Absolutely. It means understanding that there's no single magic bullet solution. You need to ask, do you need the model to think differently, to adopt a new style or skill, or to internalize very specific static patterns?
Then fine-tuning might be the answer.
Then fine-tuning is likely your path. Or do you need it to access a specific, constantly updating knowledge base for factual accuracy and currency, allowing it to stay fresh without costly retraining?
Then RAG is your friend.
Then RG is probably your friend. Your application's specific needs, its desired latency, factual accuracy requirements, how often the information changes, and your budget will dictate which path, or perhaps what combination of paths, makes the most sense. It's all about strategic design.
We've now discussed the individual innovations like MOE for computational efficiency and RAG for knowledge efficiency. But, as Rick Spear's report emphasizes, the real magic, and I mean the real challenge, is in how we synthesize these into an optimal balance for real-world applications.
That's right.
Because, as you've said, there's no one-size-fits-all answer here. This brings us to a crucial decision point in AI architecture: the compute memory trade-off.
Precisely. The concept of an optimal balance isn't some universal constant that applies to all AI. Instead, it's a dynamic, application-specific compromise. It's often visualized as an efficient frontier, similar to how economists think about optimizing a financial portfolio risk versus reward.
An efficient frontier, meaning the best possible performance for a given cost.
Exactly. There is no single best model overall. Rather, there's a curve of optimal models where for a given level of cost and latency, you can achieve a maximum level of performance. A large, dense model might offer high performance but at a very high cost. Right. A small, dense model offers lower performance but at a much lower cost. And MOE model pushes this frontier by offering significantly higher performance for a given inference cost, especially when compute is the bottleneck.
An RA.
And Aragi pushes the frontier in a different direction by dramatically increasing factual accuracy for potentially a modest increase in latency. So the choice between a traditional dense architecture and a sparse MOE architecture is a fundamental trade-off between computational cost, measured in FLOPS, and memory footprint, primarily VRAM.
That's right. We said MOE models offer significantly faster inference, leading to higher throughput and lower latency, and also lower training costs compared to dense models of the same total parameter count. But that advantage holds, provided the workload is compute-bound, right? MOE also boasts higher parameter efficiency, meaning it gets more performance bang for the computational buck.
But there's that critical disadvantage with MOE we discussed, isn't there? It seems like it comes at a significant cost of memory, which can be a real barrier for many users.
This is the critical disadvantage of MOE, as you alluded to earlier. Its primary architectural trade-off is indeed sacrificing memory efficiency for computational efficiency.
Trading memory for speed.
Exactly. And MOE model with, say, 140 billion total parameters requires the same amount of VRAM, the memory on your GPU, as a 140 billion parameter dense model. That memory requirement doesn't shrink.
Even though fewer parameters are active?
Right. Even if its computational load during inference is closer to that of a much smaller, say, 40 billion parameter dense model. This characteristic makes large MOE models quite challenging and often impossible to deploy on consumer hardware or in other memory-constrained environments where VRAM is a strict and expensive bottleneck.
So you might have the CPU or processing power, but if you don't have the raw memory to load the whole model, including all the inactive experts, you're stuck.
Exactly. You hit a memory wall first.
Okay, so while MOE is faster per token once loaded, it still needs that huge memory space. What about dense models then? Do they have any advantages beyond just being simpler to understand and maybe train?
Dense models do indeed have their advantages. They typically offer simpler and more stable training dynamics, which can be a huge benefit for researchers and engineers just trying to get things working reliably.
Less complex to manage during training.
Right. They can also sometimes show better performance in what are called I/O-bound scenarios.
I/O-bound, meaning data transfer is the bottleneck.
Yes, like autoregressive generation with small batch sizes, which is common in interactive chatbots where you're generating one word at a time. In these specific cases, memory bandwidth, how quickly data can be moved to and from the GPU rather than pure compute, becomes the bottleneck.
Ah, so how fast you can feed the active parts.
Exactly. Since all parameters are active in a dense model, the memory access patterns can sometimes be more predictable and efficient for certain operations like that. Their main disadvantages, however, are their poor computational scaling. They simply become prohibitively expensive to train and run at very large sizes.
Making them less suitable for the very cutting edge of scale.
Generally, yes.
I think that library analogy you used earlier might really help cement this compute memory trade-off. It's a fundamental concept in hardware-aware AI design.
Okay, let's revisit the library. Think of a dense model as having to physically scan every single book in that vast library for every piece of information you need.
Exhaustive but slow.
Exactly. It's incredibly thorough, exhaustive, but also incredibly slow and resource-intensive, especially for gigantic libraries. Every page, every shelf must be processed computationally.
Right.
And MOE model, on the other hand, is like having specialized librarians or experts for different subjects. When you ask a query, a head librarian, the router, quickly directs you to just a few specialists who only look at the relevant books for your specific question.
So the active work is much less.
Right. This makes the active processing of your query much faster and more efficient because only a fraction of the library is actively engaged. However, and this is the crucial part, you still need the entire library physically present for those specialists to access their relevant sections.
All the books still have to be on the shelves, taking up space.
Exactly. So while the active work is faster, less compute, the storage requirement for the entire collection, all those books, even the ones not currently being read, remains immense. High VRAM. It's a critical distinction for deployment planning.
That's a truly illuminating analogy. It really crystallizes the trade-off. Okay, now let's look at another core decision, often a strategic one for organizations. The build versus buy knowledge trade-off.
Right. How do you get knowledge into the model and keep it current?
This is truly a dilemma, as Rick Spare describes it. On one hand, you can try to build knowledge into the model itself.
Parametric approach.
Exactly. This means adopting the parametric knowledge approach by scaling up your model on massive data sets to bake in more information directly into its weights during training. What are the pros and cons of this build approach?
Well, the upside of building is the potential for incredibly fast responses on known topics, right?
Right.
Because there's no external retrieval step needed. The information is inherently within the model.
Latency could be very low.
Exactly, if the model's small enough or optimized. However, this approach is extremely expensive, both financially and computationally, because it requires those massive training runs we keep mentioning.
And the knowledge is static.
Right. The resulting knowledge is static, frozen in time when training concludes, and incredibly difficult to update for new information without another costly retraining cycle. Plus, as we discussed, the model remains prone to hallucination because its knowledge is statistical, not factual.
It's like having a brilliant but rigidly fixed brain that can sometimes confabulate.
So building means a huge upfront cost, a rigid knowledge base that quickly becomes outdated, and lingering factuality issues. What's the buy or rent option then, using RAG, and what are its advantages and disadvantages?
The buy-or-rent approach to knowledge involves using a smaller, perhaps more agile model augmented with RAG, leveraging that dynamic non-parametric knowledge from an external source.
Using the external database.
Right. This is generally far more cost-effective because you're not constantly retraining a giant model just to update facts. And crucially, it allows for real-time knowledge updates simply by modifying the external database.
Which dramatically improves factuality, trustworthiness, and currency.
Yes, all three. The primary trade-offs here are the added latency of the retrieval step before generation. It needs to go out and find the information, which takes a little extra time.
It's a slight delay.
And the operational complexity of building and maintaining that external knowledge base effectively, ensuring it's clean, organized, searchable, and constantly updated is a significant data management task in itself.
If we connect this to the bigger picture, this is like giving the AI different types of brains for different types of knowledge, isn't it? One fixed encyclopedic brain, and another that's maybe a brilliant reasoner but have instant access to the freshest information via search.
That's an excellent way to put it. Building knowledge into a model through massive parametric scaling is like giving it an encyclopedic brain that's brilliant and comprehensive within its training window, but it's fixed in time. It only knows what it learned up to its last update and struggles with anything new or outside its training. Buying or renting knowledge with ARG, however, is like giving it a smaller, perhaps very intelligent reasoning brain that's constantly connected to an up-to-the-minute, verifiable internet search engine or a curated internal one. It doesn't remember everything itself, but it knows how to find and reason over the latest, most accurate information immediately. This shift really changes the entire paradigm of how AI interacts with information.
So it's clear there's no single best model. It all comes down to a strategic decision, a framework for strategic architectural decisions, as Rick Spare puts it. It's about finding that optimal balance for a specific use case.
Precisely. The concept of an optimal balance isn't a universal constant that applies to all AI. Instead, it's that dynamic, application-specific compromise visualized as an efficient frontier.
Remind us again what that means.
There is no single best model for every task. Rather, there's a curve of optimal models where, for a given level of cost and latency, you can achieve a maximum level of performance or accuracy. The choice depends on where your priorities lie.
So if I'm thinking about deploying an AI, how do I make these strategic decisions? What are the key axes or questions I need to evaluate along to find that sweet spot on the frontier?
The optimal choice for a given application is the point on this efficient frontier that best matches its specific constraints and goals. You determine this by evaluating along several key axes. First, latency requirement.
How fast does it need to be?
Exactly. For real-time interactive applications like a live customer chatbot or maybe an autonomous agent interacting with the world, a smaller, faster model, whether it's a highly optimized dense model or a smaller MoE, is almost always preferable.
Because speed is paramount there.
Right. The added latency from a RAG system, which has to perform that retrieval step first, may simply be unacceptable for certain use cases. This raises an important question you must ask. How fast does your AI really need to be for its intended purpose? Can your users tolerate an extra, say, 200 milliseconds, or do they need an instantaneous response?
That makes perfect sense. Speed is absolutely critical for something like a live chatbot or an AI agent making real-time decisions.
Yeah.
What about accuracy and staying current? When does that trump speed?
For factual accuracy and currency, especially in applications where correctness and up-to-date information are absolutely paramount, think legal research, medical Q&A, financial market analysis, a RAG system becomes almost non-negotiable.
Because the cost of being wrong is too high.
Exactly. It provides that verifiable current information, significantly reducing the risk of costly hallucinations or outdated advice. Accuracy trumps speed in those cases.
And of course, budget always comes into play, whether it's for training or running the models. How does that factor in?
Absolutely. The computational and financial budget is crucial. For initial model pre-training, MoE generally offers the best performance for a given compute budget, allowing you to build larger, more capable models more efficiently. For ongoing inference, the running cost smaller models and MoE models are significantly cheaper to run per query than very large, dense models, which translates directly into operational savings over time.
Got it. What about the specific task domain specificity?
That's another key axis, domain specificity. Fine-tuning is essential for a task requiring a unique style, specific nuances in language, or implicit reasoning patterns not readily found in general documents. You're teaching it how to act.
Okay.
Conversely, RA is superior for tasks requiring access to a large corpus of domain-specific documents, where the information itself is the key, not necessarily a new way of reasoning about it. You're giving it what to know.
And finally, where will this AI actually live? On a massive server farm or on your phone? That must matter hugely.
That's the deployment environment, and it's often a hard constraint. For on-device or edge deployment, think AI running directly on your smartphone, a smart speaker, or an industrial sensor. Only smaller, heavily optimized models like those that are quantized or pruned are even feasible. The memory and compute constraints are just too severe.
You can't run a 100 billion parameter model on a phone.
Not directly, no.
Yeah.
But for large-scale cloud deployments with powerful, specialized hardware, then massive MoE models become a viable and incredibly efficient option.
So what does this all mean for you as you engage with AI every day or perhaps consider building it? It means strategic choices. When you encounter or develop an AI, these are the fundamental questions you should be asking because they reveal the inherent trade-offs that were made in its design. Every AI model you interact with has been designed with a specific balance in mind, optimized for a particular purpose and environment.
Absolutely. And beyond these big architectural decisions of MoE versus dense or using Rocky, there's an entire ecosystem of complementary optimization techniques that are just as vital for making AI truly practical and pushing that efficiency frontier.
Right. It's not just about the main architecture.
Indeed. Beyond the high-level architectural decisions, a sophisticated suite of complementary optimization techniques is crucial for pushing the efficiency frontier even further. These methods refine models at a more granular level, improving that delicate balance between performance and resource consumption, often invisibly to you, the end user.
Let's start with model compression techniques. What are those, and why are they so important for getting AI into our everyday devices?
Model compression techniques aim to reduce the size and computational requirements of an already trained model. making it more suitable for deployment, especially in those resource-constrained environments like mobile phones or embedded systems.
Making big models smaller after training.
Exactly. One prominent and widely used technique is quantization.
Quantization, what does that involve?
This is right, converting them down to 8-bit or even 4-bit integers, which require far less memory and can be processed faster on compatible hardware.
What's the benefit of reducing that precision so dramatically? Does it hurt accuracy much, or is it a clever trick?
It's often a very clever trick that works incredibly well. It can significantly reduce the model's memory footprint by up to 4 times for 8-bit quantization, for instance, and simultaneously accelerate inference on compatible hardware, often with minimal, almost imperceptible loss in accuracy.
Really minimal loss.
Often, yes, if done carefully. Quantization is a key enabling technology for running powerful generative AI models on everyday devices like smartphones, laptops, and even in smart home devices, without needing to send every single query to a massive cloud server. It brings powerful AI closer to you onto your device.
That's incredible. Makes sense why it's so important. And what about pruning? It sounds a bit like trimming a tree. Is that the right idea?
It's a great analogy. Pruning involves identifying and systematically removing redundant or unimportant weights, neurons, or even entire structures from a trained neural network.
Getting rid of the dead wood, so to speak.
Exactly. The goal is to create smaller, sparser models that are faster and less memory intensive, much like how removing unnecessary branches helps a tree focus its resources more effectively.
Are there different ways to prune?
Yes, there are different types. Unstructured pruning removes individual weights, which can achieve high sparsity, but can sometimes be difficult to accelerate effectively on standard hardware because the remaining weights are scattered randomly. Structured pruning removes entire channels or layers, which is generally more hardware-friendly and can lead to more predictable speedups.
Okay. And then there's knowledge distillation. That sounds like one model teaching another, maybe transferring its wisdom.
That's exactly it. Knowledge distillation is a sophisticated training process where a smaller, typically more efficient student model is trained to mimic the behavior and outputs of a larger, more capable teacher model.
The student learns from the teacher, not the raw data.
Often, yes. The student learns from the teacher's reasoning, or soft labels, the probabilities the teacher assigns, not just the final answer. This allows the nuanced capabilities, the intricate patterns, and the generalized understanding learned by a computationally expensive massive teacher model to be transferred or distilled into a much more efficient student model, which is then used for deployment.
It's a way of compressing knowledge from a giant brain into a more nimble, deployable one without retraining from scratch.
Precisely.
So these techniques, quantization, pruning, distillation, these are the hidden engineering marvels, the unsung heroes that make the AI you use feel fast, seamless, and increasingly accessible, even on your personal devices. They're doing a lot of heavy lifting behind the scenes.
Absolutely. And another critical area for efficiency, especially as we deal with longer inputs, is in optimizing the attention mechanisms themselves.
Attention, the core of the transformer.
Exactly. The self-attention mechanism, which is central to the standard transformer architecture and the very thing that made it so powerful, has a computational and memory complexity that scales quadratically with the input sequence length.
One squared, right?
That's the one.
That's
One squared. This means for very long documents, high-resolution images, or extended multi-turn conversations, it becomes a significant and expensive bottleneck. The cost explodes as the sequence gets longer.
And what are the solutions for this quadratic scaling problem in attention? Since it's such a fundamental part of the transformer, how do we handle long contexts efficiently?
Researchers have developed several more efficient attention variants to combat the scaling problem. Techniques like multi-query attention, or MQA, and grouped query attention, GQA, are very popular now.
MQA and GQA, how do they work?
They reduce this quadratic complexity by having multiple query heads share a single set of key and value projections, rather than each query head having its own independent set.
Sharing resources between the attention heads.
Exactly. The benefits are significant. They dramatically reduce the size of the key value KV cache that must be stored in memory during autoregressive generation. That's the memory of the conversation so far.
Less memory needed for context.
Right, leading to substantial improvements in inference speed and memory usage for long sequences, often with minimal impact on the final model quality. It's like streamlining the memory access needed for a conversational context or long document analysis.
We've explored the current state of play, from the foundational scaling laws and the nuanced debate around emergence to the ingenious architectures like MOE and ARGI and these complementary optimization techniques. It's been quite a journey through some seriously complex but fascinating engineering.
It really has.
But here's where it gets really intriguing. What's next for AI architecture? What breakthroughs are potentially on the horizon for 2024, 2025, and beyond? Where's the field heading?
Well, the field of generative AI is in a state of continuous rapid evolution. While the transformer architecture has undoubtedly been the workhorse of this revolution, enabling so many of the breakthroughs we've discussed,
It's been dominant for years.
it really has. But its architectural limitations, particularly that quadratic complexity of attention we just highlighted for long sequences, have spurred an intensive search for powerful alternatives. Researchers are actively looking beyond the transformer's original design.
Are there promising new architectures emerging that could genuinely challenge the transformer's long-held dominance? What should we be watching for?
Yes, there's active and really exciting research exploring novel architectures that offer more favorable scaling properties, often achieving linear or near-linear scaling with sequence length.
Linear scaling, that would be a massive leap for long context understanding.
Huge. State space models, or SSMs, such as the Mamba architecture, are showing significant promise here.
Mamba, okay.
They incorporate recurrent properties, kind of like older RNNs, but in a much more sophisticated way, allowing them to efficiently process very long contexts while maintaining high performance. We're also seeing compelling hybrid architectures like RWKV,
RWKV.
receptance weighted key value. It cleverly combines elements of transformers with recurrent neural networks, aiming to get the best of both worlds, the parallelizability of transformers and the linear scaling of RNNs.
So not just transformers anymore.
Exactly. While these haven't universally dethroned the transformer yet across all tasks, they represent a significant and growing alternative architectural lineage that could very well become prominent in the coming years, offering powerful new tools for AI developers, especially for handling extremely long sequences of information.
It sounds like the industry is also grappling more seriously now with the immense economic and environmental costs of training and running these frontier models. Is that driving a fundamental shift towards sustainability and specialization rather than just raw scale at any cost?
It absolutely is, and it's a major, perhaps the major, driving force right now. The immense economic and environmental costs associated with training and deploying frontier models, particularly the very large, dense ones, are becoming a truly major concern.
For companies, for governments?
For companies, for governments, and even for the planet in terms of energy consumption. This acts as a powerful force driving an industry-wide shift towards efficiency, practicality, and sustainability.
And what does that mean for the types of models we'll see?
This pressure suggests that the future is unlikely to be dominated by a single, monolithic, artificial general intelligence, or AGI model that does everything perfectly. That seems less likely now. Instead, the field is moving towards a much more diversified, resilient, and sustainable ecosystem of models.
A diverse ecosystem.
Yeah.
What would that diversified ecosystem of AI models look like in the real world? How would it manifest in the AI we interact with day to day?
Well, it will likely include a small number of very large general-purpose frontier models, probably built on highly efficient architectures like MoE or maybe these new SSMs, serving as foundational knowledge hubs or reasoning engines.
The big, powerful base models.
Right. But alongside these, we'll see a rapidly growing number of smaller, highly efficient specialist models. These will have been meticulously fine-tuned or distilled for very specific vertical domains, think finance, medicine, law, or even niche creative tasks like generating specific styles of music.
Models trained for one job and doing it very well and efficiently.
Exactly. They'll be incredibly powerful and efficient within their specific areas. And finally, we'll see a wide array of tiny models, heavily optimized through techniques like quantization and pruning, specifically designed for on-device and edge deployment.
Making AI truly pervasive and personal, running locally. If we connect this to the bigger picture, this isn't just about what's technically possible or what new chips are coming out, is it? It sounds like it's fundamentally about making AI practical, affordable, and sustainable for everyone, not just the biggest tech companies with the deepest pockets.
Precisely. This shift isn't just about what's technically feasible, it's becoming a strategic imperative. It's about making AI practical, affordable, and sustainable for widespread adoption across an incredibly diverse range of industries and applications. It's about moving beyond the idea that AI is confined to the labs of a few tech giants or requires massive data centers for every single task.
It's about democratizing access to cutting-edge AI capabilities in a way.
I think that's a good way to look at it.
And then there's the rise of agentic AI, which everyone seems to be talking about as the next big wave. How does that shift from simple chatbots or generators to autonomous agents impact all this architectural discussion? Does it change what kind of models we need?
The next wave of AI, which is generating immense excitement, is widely considered to be agentic.
Agents that can act.
Yes. These are not just systems that respond passively to a single prompt. They are systems that can autonomously perform complex, multi-step tasks by planning, using tools like searching the web, running code, or interacting with other software, and reasoning over a sequence of actions to achieve a goal.
Like giving AI a to-do list and letting it figure it out.
Kinda, yes. This profound shift from single-turn generation to complex, iterative workflows has truly deep architectural implications. Agentic systems require models that can be called repeatedly and rapidly within a reasoning loop.
They need to think, act, evaluate, think again, very quickly.
Exactly. Think of an AI agent that has to consider a problem, generate a subtask or a plan, execute it perhaps by calling an API, evaluate the result, and then iterate, potentially many times per second.
So this places an even higher premium on efficiency, specifically low latency and low cost per token. Because if an agent has to think multiple times to solve one problem, those costs add up incredibly fast.
It absolutely does. This places an even greater premium on low latency, how quickly the model can process one step and move to the next, and low cost per token for each iteration of its internal thought process or external action.
Which favors certain architectures.
It further strengthens the case for highly efficient architectures like MOE, the emerging SSMs like Mamba, and other heavily optimized models that can think quickly and cheaply. The brute force approach of a massive, slow, expensive, dense model is fundamentally ill-suited for the demanding, iterative, and rapid-fire requirements of an autonomous agent.
The future of AI agents relies on models that are not just smart, but also agile and economical in their intelligence.
That's a very good way to put it. Efficiency becomes paramount for agency.
This combination of economic pressure, the drive for sustainability, technological diversification towards specialized models, and the undeniable shift toward new applications like AI agents really does suggest that the future of AI will not be a monolithic arms race to build the one biggest model to rule them all.
You're entirely right. It points instead to what one might call a Cambrian explosion of architectures.
A Cambrian explosion, meaning lots of different forms emerging.
Exactly. We're going to see a wide variety of models with different sizes, specializations, and underlying designs thriving in different ecological niches. From massive models in cloud data centers processing global queries to the tiny, highly efficient processors on your smartphone driving personalized experiences right there on the device.
So diversity is the future.
It seems likely. Architectural innovation, a deep understanding of these trade-offs we've discussed, and a relentless pursuit of efficiency, not just brute force scale, will truly define the next frontier of artificial intelligence.
Wow, what a journey. We started with the foundational scaling laws, navigated the surprising debate around emergent abilities, and then moved through the ingenious architectural solutions like mixture of experts for computational efficiency and retrieval-augmented generation for knowledge currency. We then explored how these complex trade-offs are navigated in the real world to build practical AI that balances cost, speed, and capability. It's clear that the landscape of generative AI is incredibly dynamic and constantly evolving.
And to reiterate the central tension we've discussed throughout, the undeniable performance gains achieved through massive scaling are in constant, sometimes challenging, balance with the practical, economic, and now environmental necessity of computational and architectural efficiency.
It's always a balancing act.
Always. There is no single optimal balance between size and performance that applies universally. Instead, it's that dynamic, application-specific compromise determined by a multidimensional trade-off between critical factors like latency, factual accuracy, overall cost, and the specific deployment constraints of your chosen environment.
The future of generative AI isn't just about building bigger models for the sake of having the biggest number. It's about building smarter, more specialized, and ultimately more sustainable models that can power a vast and ever-growing array of new applications. From the most powerful data centers to the tiny chip in your pocket, This efficiency frontier is where the true innovation seems to be happening right now.
Which brings us to a final, maybe provocative question for us all to consider. As AI continues to specialize and integrate really into every facet of our lives, from smart assistants anticipating our needs to highly specialized, industry-specific tools reshaping entire professions, how will our own relationship with knowledge, information, and problem-solving evolve alongside it?
That's a deep one. How do we change as AI changes?
Right. Will we become more specialized in our own learning, relying on AI for breadth? Or will we become more adept at leveraging these increasingly diverse and sophisticated AI tools as extensions of our own capabilities, becoming better generalists or integrators?
Powerful questions for us all to consider as we navigate this rapidly evolving landscape. So what does this all mean for you as you observe, use, or even build with AI in your daily life? We encourage you to continue your own deep dive into these fascinating topics.
Keep exploring.
We'll catch you on the next deep dive.